Alright, so for our next problem, we're going to be looking at things related to the frictional heating and in particular the fanning friction factor. And I have the equation that relates frictional heating to the fanning friction factor up here. That will be relevant later. But to start, we're going to be looking at a vertical tube that has liquid flowing through it. So you can think of this more as like if we had like some sort of tank and it had a pipe, and there was some liquid in it, just flowing out into the atmosphere. So open on both ends to the atmosphere and such. So in particular, we're going to look at some amount of liquid within this tube, because this tube is just like a smaller, a zoomed in version of this pipe. So we're going to be looking at that, and the column of liquid that we're looking at is going to have a radius of small r, whereas the radius of this entire pipe is going to be big R. Okay, so what do we know about this column of liquid? We know that it is not accelerating. So we have no acceleration, and therefore our net force on this column of liquid is going to be 0 as well. So we can do a force balance for this. So what forces are acting on this? We have, gravity, so we have the weight of the fluid, and then we also have shear stress from the other fluids surrounding that fluid that's going to be pushing it up. So our downwards force is going to be our weight, and our upwards force is going to be that shear stress. So let's start with the weight of the fluid. So as in my last video, weight is going to be equal to, the density times big volume, not big volume, big V, which is volume, times acceleration due to gravity. So we're going to have that the density of the fluid times the volume of that fluid times little g. That's the weight of the fluid. And we can expand this a little bit, and we'll have density of the fluid, and then the volume, which will be volume of the cylinder, which is pi r squared over the height. So the height we're going to have as delta v. So times pi r squared delta v times little g. Okay, and that's so then that's plus the shear stress force. So that's going to be shear stress times the area over which that force is acting on. It's going to be equal to 0, because that's our net force. So the area that shear stress is acting on is going to be the surface area of the cylinder, which is 2 pi r times the height. So 2 pi r delta z. So just the surface area of that, the outside columns, not including the circles on the top and the bottom, because we're really just looking at like that concentric circle. Alright, and then that is going to be equal to 0. Okay, so next thing we can do is we can substitute for shear stress. We know that by definition shear stress is viscosity times dV dr. So we put that in. This term remains the same. Well, actually, we can cancel some things too. So pi is going to cancel those two, and then delta z will cancel, and then one of these r's is going to cancel. All right. So we have density of the fluid times R times G plus, and then for this we're going to have mu times change in velocity over the change in radius times 2 is equal to 0. Okay, so now you can see we're going to need to take an integration, but first we have to get this over by itself on one side. So we're going to have dv dr is equal to, so subtract this term over, we've got negative density of the fluid times the radius times the acceleration due to gravity over 2 times mu. Okay, so now at this point we can take the integral, and we're going to be doing this by constant of integration, so I'm not going to define the limits at this point. So we're going to have the velocity is equal to, we can pull those outside, we've got density of the fluid times acceleration due to gravity over 2 mu, because those are constants, so then we just have the integral of r, I forgot, never mind, because that dr is over there. I'll rewrite that. That's confusing. Okay. And then it's going to be integral of r dr. So multiply that over to the other side, and then we're going to do this by constant of integration. So then we have velocity equal to negative density of the fluid times acceleration due to gravity over 2 mu. Integral of that is r squared over 2, and then plus c for constant integration. Alright, and so then we're going to need to know what is c. But there is one point along here that we do know the velocity for, and that is when little r is equal to big R, because the tube's not moving, so there's no velocity there. So, so we can substitute that in, and do this in blue so it doesn't get confusing. Alright, so then we'll have that 0 equal to density of the fluid times acceleration due to gravity over 2 times the viscosity, times big R squared over 2 plus c. So we solve that for c. C is equal to density of the fluid times acceleration due to gravity over 2 times density times big R squared over 2, and then we can plug that in there. And so we've got that our velocity is equal to negative density of the fluid over acceleration due to gravity over 2 mu times little r squared over 2, and then plus c, which is the density of the fluid times acceleration due to gravity over 2 mu times big R squared over 2. And you'll notice we have some commonalities between these two terms, so I'm just going to factor them out. And so we've got that velocity is equal to density of the fluid times acceleration due to gravity over 4 mu, so 4 is from that 2 times that 2, times big R squared minus little r squared. Okay, so there we have an equation for the velocity. So what can we do with this? So we can look at this in terms of the flow rate next. So go up here, we'll have that Q is equal to the integral of velocity over the change in area. So we can plug that in as is, but area is obviously not in this. We're going to put area in terms of radius. So the area is plug that in for the area and this in for velocity, and we'll have that Q is equal to the integral of density of the fluid times acceleration due to gravity over 4 times the viscosity times big R squared minus little r squared times 2 pi r dr. Okay. So then, what are our limits of integration? So we're going to be integrating from, like the very smallest that we can have to all the way to the edge of the pipe. So that's from 0 to big R. And, alright, so we can simplify this a little bit. So, this all can be pulled out of the integration, that can be pulled out of the integration. So, this 2 cancels with that 4. So we're going to have density of the fluid and acceleration due to gravity times pi over 2 mu, and then integral from 0 to big R, and then we're going to factor this R into the parentheses, and we'll have r squared little r minus little r cubed dr. Okay, so then, alright, so next, carry out the integration. This part's the same, and then we're going to have big R squared, little r squared over 2 minus little r to the 4th over 4, evaluated from 0 to big R, and this part's still the same. And then that will be, so plug in big R for little r, so we've got r to the 4th over 2 minus big R to the 4th over 4, and then we plug in 0, which will give us 0, so that's it. And then again, we can simplify that Q. So the flow rate is density of the fluid times acceleration due to gravity times pi. I do not know why I wrote pi there, that's a mu, over 2 times the viscosity, and then this is essentially a half minus a 4th, which is a 4th, 2 times r to the 4th over 4, and then we can combine those two, and we've got that Q is equal to the density of the fluid times acceleration due to gravity times pi over, or times r to the 4th over 8 mu. Okay, so then that is the equation for our flow rate. Alright, so now we've got an equation for the flow rate, and next thing we're going to want to start to do is start incorporating this into an equation for the frictional heating, because that's eventually the direction we want to go in. And the only equation that we know that has the frictional heating in it is the Bernoulli's equation, so we're going to start with that. So Bernoulli's equation is the pressure at 2 minus the pressure at 1 over the density, which in this case is the density of the fluid, plus velocity 2 squared minus velocity 1 squared over 2, plus delta V times G, which is equal to the negative of the frictional heating. Alright, so then, in terms of our problem, we're going to look at this. The pressures are not different from the top of our tube to the bottom of the tube, because we are not in a static container. If we had like a bottom on the bottom of this tube, then yes, pressure would change with depth, but since the fluid is moving and not static. That's not the case here. So pressure, it's open to atmosphere on both sides, so pressure is the same on both sides, which means pressure throughout this whole tube is the same, so there's no change in pressure, meaning that this term goes to 0. The next term we have has to do with velocity, and velocity within this tube would only change if the size of the tube changed. So since this tube is not getting any smaller or any bigger, our velocity is not changing. And therefore, this term is also equal to 0. And so we're left with just gravity-driven flow, which, we could already kind of think about mentally. Yeah, it's just being driven by gravity. There's nothing else really causing this to flow other than gravity. So, got our gravity-driven flow, and then we've got our equation for flow rate. And we can combine these two equations by the one variable that they have in common, acceleration due to gravity. So we have to solve this for acceleration due to gravity first, and we're going to plug it in up here. So we're going to have acceleration due to gravity is equal to 8q times mu, and multiply that over, and divide this stuff over rho fluid times pi times r to the 4th. And then there's also one other thing we're going to want to do. We have radius here, but eventually we're going to be combining this with a term with diameter in there, so we're going to want to just convert this to diameter so that, we have consistency. So our radius is equal to diameter over 2. So we plug that in, raise it to the 4th power, multiply by that 8. So we've got that acceleration due to gravity is 128 times q mu over density of the fluid times pi times d to the 4th. And we can plug that in all the way up. So we've got that 128 q mu times delta z over density of the fluid times pi times d to the 4th equal to the negative of the friction factor. So we're going to need to be careful about our signs here. We have this negative sign here, and then we've also got this delta z that has a sign, within it that we didn't really discuss before, but this delta z is essentially the negative of a length, because we would set like 0 up here and like delta z, or if you want to go for just like length down here. So it, positive is that direction, so it would be a negative length. So I'm going to switch this out for a negative length, and therefore those two negative signs would cancel. And so we've got that the friction factor is 128 times q mu L over density of the fluid pi d to the 4th. Okay. So we have this equation that has frictional heating in it, and this equation that has frictional heating in it. Both are solved for frictional heating, so we can set the right-hand sides equal to each other. So we've got that right-hand side, we've got 4 times friction factor times, okay, so up there it's delta z. I'm going to change that so it's consistent to be L. Because we know that the sign's taken care of there. Okay. So times L v squared over 2d is equal to 128 q mu L over rho f pi d to the 4th. Alright, so now we have some things that can cancel over here. Our L's are going to cancel, and then our numerical constants can combine, so this is 2, 128 divided by 2 is 64. So we've got b squared over d equals 64 q mu over rho f I d squared. And then we can substitute in for q. We know that q is equal to velocity times area, and we know that our area is, it would be the cross-sectional area, so pi r squared. So then we can plug that in over here. But we don't want r, we want this in terms of d, so q is equal to v times pi d squared over 4. Alright, so we're going to plug this in, and I'm going to simplify. I'm just going to plug it in, and then we'll deal with it. Okay, so we got f v squared over d is equal to 64 times q, so v pi d squared, and this mu over 4 rho of the fluid pi d squared. Okay, and then this is d. I don't know why it says d squared. Okay, so then we can have. So then it's just a matter of simplifying things. We've got 64 divided by 4, which is 16. We've got d squared, or we've got these pi's right here. D squared over d to the 4th, and then times the d, so then that's just d to the 1. And then that velocity cancels. Okay, so we've got that our friction factor is equal to, okay, so we've got our friction factor is equal to 16 mu over v rho f and d. Alright, so then you'll notice that mu over v rho d is equal to 1 over our Reynolds number. Just by definition of Reynolds number, so we can put Reynolds number in there. And we've got that our fanning friction factor is going to be equal to 16 over our Reynolds number. And so there we have an equation for our fanning.